All right, good afternoon.
Did we just push class back like 17 minutes so I can finish this video?
What video are you watching?
Some random garbage.
Oh.
No?
Probably not.
Uh,
I don't know. Random garbage, discrete structures, it's a toss-up. All right, so hope everybody's doing well. Any questions?
I have a question.
Yeah.
On the homework, Fermat's little theorem, question 2. I was able to solve it, but I don't know if I did it right. I somehow came out with the right answer just by kind of doing things, and it just kind of ended up working, but
So let me.
like a trillion steps, and I am not sure if I did it right.
So I'm looking to see my copy of the homework. Fermat's little theorem: 2 to the 6002 mod 7.
Correctamundo. So the answer was 4, but the way I got there was quite bad.
So Fermat's little theorem tells us one thing. It says in general, it says a to the p minus 1 is congruent to 1 modulo p. As long as a is not congruent to 0 mod p, because if a is congruent to 0, then any power is also congruent to 0. But as long as a is not a multiple of p, a to the p minus 1 is congruent to 1 mod p for pretty much any a. And we have a question that's asking about something modulo 7, and 7 is prime, so that's a good reason to think Fermat's little theorem. And you know, bonus, we were told to use FLT. So what does Fermat's little theorem say about the prime 7? It says anything raised to the 6th will be congruent to 1 modulo 7. And we're asked a question about powers of 2, and so the application of Fermat's little theorem to this problem most closely is 2 to the 6th is congruent to 1 modulo 7. And we can confirm that if we want. 2 to the 6th is 64. That's 1 more than 63, which is divisible by 7. 9 times 7 is 63. So we could find this fact ourselves by trial and error, but FLT tells us directly that this is true. Well, there's this law of exponents, which says, you know, a to the b times c is the same thing as a to the b raised to the c. Because this means take a to the b, multiply by itself, you know, c times, and so that's a to the b times a to the b times a to the b, it's a to the b times c. That's fun to say. So 2 to the 6th is also, 2 to the 6th is congruent to 1. 2 to the 60th is the same as 2 to the 6th raised to the 10th. 2 to the 600th is 2 to the 6th raised to the 100th. 2 to the 6,000th is 2 to the 6th raised to the 1,000th. This has nothing to do with modulos. This is just, you know, plain numbers. And so 2 raised to, you know, any multiple of 6 is going to be 2 to the 6th raised to the x. So once we know 2 to the 6th is congruent to 1, we know something about 2 raised to any multiple of 6.
It's 1.
It's 1, right? Exactly. So 2 to the 6,000th is 2 to the 6th raised to the 1,000th. which is congruent to whatever 2 to the 6th is, raised to the 1,000th, and 1 to the 1,000th is just 1. It's 1 multiplied by itself 1,000 times. And so we just leapfrogged all the way up to 2 to the 6,000. And we're trying to figure out 2 to the 6,000 too. Well, just multiply by 2 twice. So 2 to the 6,001 is 2. 2 to the 6,002 is 2 times that previous, which is just 4. And so there's your answer. So modular exponentiation is nice when we don't have, you know, something like this, but we can find in this leapfrog fashion 2 raised to the 1, 2, 4, 8, 16, 32 powers of 2, and then multiply those together so that the exponents add up to whatever our desired exponent is. But FLT kicks in sometimes if, you know, we're working modulo a prime, and if p minus 1 goes into this, you know, mostly an integer number of times, we can sort of jump up to that by doing 2 to the p minus 1 or a to the p minus 1 and scaling it up by whatever we need. So that's useful.
I did this in like 4 million steps and very badly. So.
Okay, but you got the right answer, right?
Right.
And you got to do some modular arithmetic.
Yeah.
So that's.
So I did the whole AP minus 1 equals 1 mod p.
Mm-hmm.
And then I got, you know, 6 equals, or 2 to the 6th equals 1 mod 7, and then I used that, but I just did like 4 trillion steps to get down to the
okay.
next one, instead of just doing it 2 to the 6th, 2 to the 6,000.
Right, right. So okay, but good, but you knew what Fermat's little theorem was.
Right.
And you were able to state what that says, and then it's just a question of knowing how to use that as a shortcut. So it sounds like you've got that now. Cool. Other questions?
So, wouldn't you have to make the 4 congruent to, 4 congruent to 3, since it's mod 7?
4 is not congruent to 3. So, because 4 divided by 7 is actually 0 with a remainder of 4. But 4 is actually congruent to minus 3. Right? Because if you take 4 and minus 3, their difference is 7, which is a multiple of 7.
Okay, thank you.
That's a really easy mistake to make. Don't feel bad about that. And this is where, you know, when I say show your work, because it can help with partial credit, that's a really good example of it, right? If you did all of this and you got all the way up to here, and then you wrote down, you know, congruent to 3 and circled that, that's just, you know, a misstep there at that last part. But the point of the problem, Fermat's little theorem, exponents, all that, you got all that, right? So you might not even lose points. I might just, you know, circle it and say, you know, don't do that last thing. But if you do all this on scratch paper and then you just write down a 3 and it's wrong, right, there's no opportunity for partial credit there. So that's a good example of showing your work and how it can help. Cool, what else?
Could we take a look at the programming assignment? Like,
sure. You have particular questions about it?
no, I mean
Like an example solution?
yeah, sure.
Wonder if I've got any. So here's an example. this is from a few years ago, so I can't vouch for this. But so I'm writing a function called gold, and gold will take an even integer and print out that integer as a sum of two primes. Notice my complete and utter lack of commenting in this program. This is not a good example. So
What is it called? Gold?
gold for Goldbach.
What's Goldbach?
That's what we were doing in PA1. Goldbach's conjecture is the conjecture that any even number can be written as a sum of two primes. So, there's my nod to good commenting. All right, so gold is a function that takes an integer and tries to print it as a sum of two primes. So what do? I generate odd numbers between 3 and my number divided by 2. So I start at 3, go up to num over 2, and I increment by 2's. And if that number I is prime, and if the number I'm working with minus I is also prime, I have a solution. My original number is just I plus num minus I. If I were to get all the way through here and not find a case where I is prime and num minus I is prime, I have found a counterexample to Goldbach's conjecture. I'm now, X million dollars richer. So print out a message and just exit. And then how do we tell if a number is prime? Well, there's a lot of ways, but here's one example. B is my tentative divisor. A is the number I'm testing. X is the quotient, and I iterate as long as B is less than or equal to X. Now, why am I doing that? If I'm doing X equals A over B, if I'm doing B less than or equal to X, that means B is less than or equal to A over B. Everything's positive. That means B squared is less than or equal to A. That means B is less than or equal to the square root of A. So this is a way to know when to stop my test, thank you, without having to calculate square roots and deal with floating points and all that kind of stuff. So while B is less than X, I check to see if A is divisible by B. How do I do that? Well, X will be the integer I get when A is divided by B. So just see if X times B is equal to A. If it is, then A over B must have been an int, and so I can return 0. Otherwise, increment my possible divisor, recalculate X, and keep looping. If I come out of this loop at the bottom, my number was prime, and so I can return that. So there's a prime number tester. There's a loop that checks Goldbach's conjecture for an even number. And then here's a loop that calls Goldbach's conjecture from my 5 million to 5,998.
I way overcomplicated this.
That's okay. You probably didn't get a million warnings with your program, but it works.
You said, sorry, I didn't hear what Lindsay said.
I just said I overcomplicated it, and that was about it.
Oh, I see, sorry. I thought you said something else.
So, in my interpretation, shorter code is not necessarily better, right? Code that makes sense to you is the best possible code. And a lot of times when you start developing a program to do something, you start off with an idea, you write some code, it doesn't quite work, so you add some things, it works a little better, but you find some edge cases that don't work, and so you add some more code to deal with those. And when you're done, you have something that works, right? But you look at it and it's got all this stuff inside, right? That's kind of a picture of the organic development of the program. And a lot of times, if you go away from it and come back later, you might think, oh, I could do that a whole lot more simply. And, you might go back and rewrite it if this is something that you're going to use down the road and so on. Um, but I don't think that's a necessary goal, particularly when you're learning something, right? Your goal is to understand, and you know, it's kind of a record of how you got to that solution, and that's got value in itself, because it's not just the final code that's written in a few lines that works perfectly. It's I tried to do this and I forgot about this case, and so I did this other thing to take care of that, and so on, and that's critical for getting better at programming. This prime number test that I've got here, I wrote this the first time probably over 45 years ago, right? I mean, I was a punk in high school, and I worked on this a lot, and I kept beating it down to a simpler and simpler and simpler version. I got down to what I thought would be, for the machine I was running on, the simplest, fastest version of a prime number generator. And this is not an obvious way to test for primes, right? If you do this in 121, you use a much more direct pair of nested loops or whatever, right? So I wouldn't be too worried about if things seem like they're overcomplicated. In general, I think that's often better, because it more.
It just returns the next prime or something.
This tells you whether or not a number is prime. So it returns 1 if it's prime, 0 if it's not.
Oh, I see. Let's see here.
But it has 1 division, no square roots, and all integers.
So how does it do no square root? Yeah.
So it's doing no square roots by checking to see if b is less than or equal to x, which is the same thing as b is less than or equal to the square root of a.
I do have a quick question.
Yeah.
Oh, wow.
In the code, it was intended for us to be able to put in any number and then any length of iteration, correct?
I think so, yeah.
Okay.
But I really mostly care about seeing the output and the code, so something like this. Because that's the part of the program that relates to what we were doing with number theory and primes and all of that stuff.
Yeah, no, mine's wrong.
I think yours was right.
My output is way wider than this.
And I don't know if I actually said to take in arbitrary numbers, but the essential part of the requirement was say again?
You said to take in a starting number and how many to test.
Okay.
I was confused with the instructions at first and instead did a starting number and test till this number.
That's fine. It's the same thing.
And then I had to re-scrap the entire thing because I had to do it a little differently. Because
Okay.
I had to do iterations of this number
Ah.
versus up to a number.
Okay.
But yeah, I fixed that and that took hours.
Okay.
Modularity helps with that though, because then you can kind of reuse code.
Yeah, in some way, shape, or form, if you can break it into pieces, it makes it easier, right? Because my main program just calls, my Goldbach function. And my Goldbach function, if I have a way to tell if a number's prime, it's really just one for loop. And then to tell if a number's prime, that's a separate loop. But if I tried to put this, inside my main program becomes, more cumbersome. So that's a quick way to modularize. All right, good. Any other questions?
I forgot what Goldbach's conjecture was and wrote it to work for every single number.
Oh, okay.
Didn't actually work, but so I was confused for a little while until I remembered it's just evens.
Yeah, so why doesn't it work for odds usually? Anyone got an idea?
You add 2 odds and it's always an even number.
Yeah. So if you try to write, 101 as a sum of 2 primes, well, 2 is a prime, but 101 minus 2 is 99. That's not a prime. 3 is a prime, but 101 minus 3 is 98. That's not prime. 5 is a prime, but 101 minus 5 is 96. That's not prime. And in fact, any odd number I subtract, I'm going to end up with an even number. And unless that even number is 2, we know it's not prime. So in general, this won't work for odd numbers unless they're exactly 2 more than a prime. Even numbers, though, totally different story. Very hard to find an even that can't be written that way. All right, so let's go back to the thing I left you with on Monday. We did an inductive proof that n is equal to n plus 1 for all integers n bigger than or equal to 0. Oh, I think I did n bigger than or equal to 2. And so we had this nice inductive proof. We assume p of n, which means n equals n plus 1. We add 1 to both sides. That tells us n plus 1 equals n plus 1 plus 1. That's p of n plus 1, and so pn implies pn plus 1. And therefore, pn is true for all n bigger than or equal to 2. So have we just proven that 2 equals 3? Which would basically break everything. Or maybe it does.
No, 2 doesn't equal 3.
If it does, everybody's got 100 in here, because whatever grade you have would be equal to the next grade up, and you could keep inducting, and eventually you'd show your grade was equal to 100. So that would be kind of cool.
Yeah, that'd be awesome if we could prove our grades using bad math.
Yeah. On the other hand, everybody would have a 0, because 0 would also be equal to 100. So that wouldn't be so good. So what's wrong with this proof?
The proposition's messed up.
This proposition?
That's wrong.
But how do you know it's wrong? I just proved it's true. How do we know that the proposition that the sum of the first n integers is equal to n times n plus 1 over 2? Maybe that looks messed up to me. But if we can do an inductive proof and show that that proposition is true, it's a true proposition. Even if I don't like the way it looks or it seems obviously wrong to me. And if we have to discount mathematical induction when the thing we're trying to prove just looks wrong, then this isn't a very useful tool.
So is it wrong or is it right?
Yeah. I mean, this proposition, n equals n plus 1 for all n bigger than or equal to 2, this cannot be right. It's got to be wrong. But I've applied mathematical induction and proven it's true. So what went wrong in here?
Using algebra.
We're allowed to use algebra. So think back to the other inductive proofs we've done. And what do we call this step when we prove Pn implies Pn plus 1? We've had a name that I keep using for that. Do you remember what that name is?
The base case?
This is actually the inductive step. So what is the base case? What do we usually do in the base?
Isn't it like prove n equals 2 primes is true?
So the base case is proving p for a particular value, for example, for 2. So the base case would be something like prove one of these propositions, prove that P of 2 is true, for example. And I never proved a base case in here. I proved the inductive step, and that's a absolutely perfect proof of the inductive step. There's nothing wrong there. But to apply mathematical induction, you need two things. You need the inductive step, but you also need a base case. And I never proved a base case. And in fact, I cannot prove a base case because P of 2 is not true. P of 2 is the proposition that 2 equals 3, and that's false. P of 1 is not true. P of 1 is the proposition that 1 equals 2, and that's not true. So I have an inductive step that's been proven, but I don't have a base case. And without both of those things, this does not apply. I move from here to the conclusion that P of n is always true by saying I've shown the inductive step and I've proven a base case. You got to have both of those. And the base case is usually so straightforward that we just kind of, put it in the top of the proof and we don't think a whole lot about it. But if we forget to do that, we can come up with some really crazy results. So you got to be able to prove a base case. And if we could prove, a base case, if we could prove that 1 equals 2, yeah, we could prove that 5 equals 6, right? Because if 1 equals 2, just add 4 to both sides, 5 equals 6. And so if 1 equaled 2, we could prove that, n is always equal to n plus 1. But since we can't prove that for any particular case, this inductive step doesn't get us anywhere. This is the ladder that reaches to the moon, but we can't climb to the moon because we can't get to the start of the ladder because it's sitting, outside the atmosphere. We've got a ladder that we can go from one rung to the next and eventually get to the moon, but we can't get to that first rung. We can't start the set of chain rules that we would use to eventually prove, P of 1,000 or P of 1,000,000 and so on. All right, so I posted some homework on Canvas related to mathematical induction. And let me just hop onto Canvas. So we're working on sections 3.4, 1, 5, and 6, and 3.5, 1, 8, and 9. And these are coming from the additional CSE215 text. So you can get to that through the front page of Canvas. And so here's the additional CSE215 text. This is a book of problems. So our spiral workbook for discrete mathematics. Yeah, the zoom feature is kind of weak on. All right.
I'd say Zoom's pretty garbage.
Yeah. So 3.4. And I have this downloaded. I'll switch to that if we need to. All right, so I'm going to give up on Canvas and just go to a PDF. So chapter 3 is talking about proof techniques, and it's got some work on induction. So let's go to 66. All right, so 3.4, mathematical induction. And you know, you're welcome and encouraged to read through this. This is another presentation of the idea. And it starts with the same example that we used, sum of consecutive integers, and it talks about the base case and the inductive step, and so on. And there's some examples worked out. There's a sum of squares, right? Here's a weirder example, still algebraic, but you know, kind of bizarre. Sum of 3 plus 5i plus 3 equals this interesting looking formula. So you can work through those. And then there's exercises at the end of that section. So from this section, questions 1, 5, and 6. 1 is looking at the sums of cubes and showing that the sum of the first n cubes is this formula. And this is an exercise in algebra, right? And don't try to do this in the margin of a piece of paper. Give yourself a big clean sheet of paper and be prepared to rewrite this a few times. There's the process of mathematical induction, which is, you know, writing out the family of propositions, proving a base case, stating the inductive step, stating the hypothesis, defining what it is, and so on, right? And then there's the actual legwork of how am I going to go from P of n to P of n plus 1. And that's going to involve, you know, plugging n plus 1 in here, so doing n plus 1 squared times n plus 2 squared divided by 4, and relating that to this expression. And it's going to take, you know, a lot of multiplying polynomials, simplification, comparing one thing to another, and you probably won't fall into the right set of steps the first time you try this. But, you know, scratch paper, whiteboard, whatever, work through this until you feel like you have gotten to what you're trying to do. You've gotten to P of n plus 1. And then go through your work and see if you can find the direct path from P of n to P of n plus 1, a more direct path, and write that up into your proof. And remember, it's a formal proof, so don't just be writing equations and, you know, start with one equation, get to the next one. Each line of your proof has to be a proposition. This is a proposition. It's the statement that this is equal to that. This that I've highlighted is not a proposition. It does not have a truth value. Just like x squared does not have a truth value. 17 does not have a truth value. But x squared equals 17, that's a proposition. That can be true or false. So make sure every line of your proof is a proposition, and then work through and show each line follows from the previous lines. So that's the first question, is the sum of cubes. Question 5 is looking at I times I factorial. Adding those up. And the best thing I can say here is just remember what factorials are. N factorial is 1 times 2 times 3 times n. It's the product of the first n integers. And a useful thing to keep in mind is that n plus 1 factorial is n plus 1 times n factorial. Product of the first n integers times n plus 1, that's the product of the first n plus 1 integers. And this, or other versions of this, are really the trick to making that proof work out. Another version of this would be n factorial equals n times n minus 1 factorial. It's exactly the same thing. Sum of the first n minus 1 integers times n, that's the sum of the first n integers. So keep those in mind and play around with it, and you should find a way to do this one, number 5. And then number 6 is another exercise in algebra, except this time we've got, you know, things on the bottom. But we should be able to show that this sum is equal to this expression. And these are puzzles. These are not something that if you just follow the steps we've done in class, you're going to get to the answer. Because there's always this piece in the middle where it's like, how do we go from here to there? And that's the puzzle part. That's the trial and error part. but it's worth spending some time and energy on that trial and error part to see how to make that bridge from one step to another. And then, as I've said, usually all the stuff before that is boilerplate, all the stuff after that is boilerplate. It's really that one transition in the middle that that's most tricky. And you're welcome to try some of these other ones. This one's not bad. This one gets into powers of -1 or -3, right, to alternate plus and minus signs. But if you want extra challenge, right, that's a fun one to play with. So those are 3 questions from 3-4, and then 3-5, 3 more questions. And so questions 1, 8, and 9. So question 1, prove that this is a multiple of 3 for all integers n bigger than or equal to 1. And you got to use induction. If we use modular arithmetic, this is pretty straightforward. But do this using induction. In other words, prove that if this is true for n, then n plus 1 times n plus 2 times n plus 3 is also a multiple of 3. And then questions 8 and 9 are about inequalities. Show that n factorial is bigger than 2 to the n. We kind of did that the other day. And then prove that n squared is bigger than 4n plus 1 once you get to 5 or higher. So a reminder that Monday is a holiday, so we won't meet again until a week from today, which is when this homework is due. So you're going to want to use office hours, right? Work on this, sooner rather than later, and then come by office hours if you're getting stuck. And that's probably the best way that I can help you. I can go through more examples in class, but watching is not going to be as effective as doing. And so you need to start doing these proofs and working on them, and when you get stuck, I can try to point you in a direction to get you unstuck. And that's the best way to learn these. All right, so questions on any of that?
I'm sure there will be.
Fair enough.
I'm actually kind of confused about this. N plus 1 exclamation mark is equal to n plus 1 times n exclamation mark. Because the formatting, that doesn't seem right to me, and I just am like, where did that multiple of n exclamation mark come from?
All right, sorry, which number was that?
Not number, you just took the paper away.
Oh, the thing that I wrote down.
Factorial. Yeah.
So this thing?
Yeah.
Ah, okay.
I keep looking at it and I'm like, how did you come up with that? Is there a law that I'm missing?
So let's do it like this. N plus 1 factorial. This is a shorthand for the following expression. 1 times 2 times 3 times 4, and so on, times n minus 2 times n minus 1 times n plus 1. Right? That's what it means. It means multiply the first n plus 1 integers. Okay with that? So n factorial if we do the same thing, is just the sum of the product of the first n integers. And so all I'm doing is noticing that this and this are exactly the same thing. And so if I rewrite all of this as just n factorial, that tells me n plus 1 factorial is n factorial times n plus 1. which is the same thing I wrote, just with these in the opposite order. And that's how most of these things work, is if you write out explicitly what a factorial is, sometimes you can find some part of that you can express as a different factorial. And that's what's going on in here.
I don't know if my brain's just broke or something, but that made no sense. I'm wondering if it's because I'm looking at it as math versus something that it's not supposed to be math.
So does this first line make sense?
No, not at all.
Okay, so that's the definition. So for example, 6 factorial is 1 times 2 times 3 times 4 times 5 times 6.
That makes sense.
Okay, and if we multiply that out, that's 6 times 4 is 24, times 5 is 120, times 6 is 720. All right, 5 factorial is 1 times 2 times 3 times 4 times 5, which is 2 times 3 is 6, times 4 is 24, times 5 is 120. If I take this and I multiply by 6, I'm guaranteed to get that. Because 6 factorial is this thing times 6, 5 factorial is just this thing. So if I take 5 factorial, which is this, and I multiply by 6, that's this, which is 6 factorial. And it may not click intuitively why that's true, but it comes out of the math, basically.
Okay. I can see it now that you've put numbers in it.
Okay.
It's just really hard to like come to terms with it in the placement of just like n, I guess. That's weird.
Okay. Maybe try some other numbers, right? Like try 4 factorial as this, which is 24. 3 factorial is this. And so if I take 3 factorial, right, which is this piece, and I multiply by 4, suddenly I get 4 factorial. And try that with a few other numbers, and I think it'll start to click a little more. And the way we get to things like this with n is by generalizing, right? Usually we do this with specifics for a few cases, and after enough cases you start to see why, oh, it doesn't really matter if I do a 4 or I do a 6 or I do an 8. I can do this for any number and still do the same kind of trick. And then this is just, you know, writing that trick in a general form. But it builds out of, you know, looking at specific cases first.
I think something just connected because I can now figure out why we've just been proving n equals n plus 1. And now I understand why that is relevant, finally.
Okay, cool. Awesome. Very good. All right. Anything else? All right. Let's go on and talk a little more about recurrence relations, which I think I spelled wrong. I think it should be an E. So a recurrence relation, we've tapped into this in CSE215 a few times. We've touched on it in here. It's this idea of defining something in terms of, you know, another version of the same thing. And so one way we can do this is with factorials like we just did. N factorial we can write as n times n minus 1 factorial. Sum of the first n minus 1 integers times the nth integer gets us n factorial. And so if we wanted to write a function named factorial, we could just return n times factorial n minus 1. And it's a relation that, you know, the description of this function is given in terms of an expression involving this function. Right? So that's a recursive definition. Or this is a recurrence relation. And if we just try to run this is going to blow up. We're going to keep calling this function for different values of an argument, and eventually we're going to run out of memory. And so we need a base case here. We need something like if n equals 1, return 1. And so we could actually write n factorial is equal to this if n is bigger than 1, and it's equal to 1 if n equals 1. And so now we've got an expression of n factorial in terms of, you know, in general, another factorial, or for a particular value of n, we've got an actual value. And so I think we played around with this a little on Monday. Where we wrote a recursive function. I used 0 as a base case here. I could use 1. So if our number is 0, we return 1. Otherwise, return n times factorial n minus 1. And this correctly calculates factorials. And it's just using this expression. So there's 2 factorial, 3 factorial. There's 4 factorial, 5, and so on. And recurrence relations pop up in a lot of different situations. And so, where do I want to go with this? So let's think about a colony of bacteria. And suppose we have a colony with some number of bacteria in it, and we understand that the population doubles every hour. So bacteria multiply over time, and let's say that every hour the population doubles. We can capture this with a recurrence relation, so let P of n be the population at time n. Red alert here, we're not talking about propositions anymore, right? We're talking about a mathematical function p that takes a number n, which is a number of hours, and returns the population of bacteria at that time. It just happens to be that we've been using P of n for a few weeks as propositions. But this is a mathematical function. Okay, so it's not a proposition. It just looks like one. Well, if we know the population doubles every hour, and n is a time in hours, we can write the following fact. The population at time n plus 1 should be twice the population at time n. It's a recurrence relation. And if we know that the population at time 6 hours was 100, we can figure out that at 7 hours the population will be twice that, which is 200. But we can't actually use this to find the population because we're missing something. If we want to know what the population at time 0 was, all that this tells us is the population at time 0 would be twice the population at time -1. And that doesn't make sense, right? We can't find the population before the bacteria was being considered, right? So we need a base case. So our base case might be, for example, P of 0 equals 10. Now, with these two pieces of information, we know everything there is to know about the bacteria population. We know that the initial population was 10 at time 0. We know that at time 1, the population would be twice that, which would be 20. And so we can start finding values of this function. We could say, for example, P of 1 is twice P of 0, which is 2 times 10, which is 20. And if we want to find the population at time 2, that's twice the population at time 1, and we just found P of 1 was 20, so this is 2 times 20, which is 40. And we'll go one more and say, what's the population at time 3? This says it's twice the population at time 2. And we know that at time 2, the population was 40, so this is twice 40, which is 80. And we could work up and we could find the population, at time 100 if we wanted, by doing this, 97 more times. But we may be able to find a formula for describing what P of n is as a function of n. And can anyone see or postulate a formula for what P of n is that's not a recurrence relation?
2 to the n P of n.
So 10 times 2 to the n.
Yeah.
Right? So if n is 1, this is 2 times 10 is 20. If n is 2, this is 2 squared is 4 times 10 is 40. If n is 3, this is 10 times 2 cubed is 80. And so this is called a solution to this recurrence relation. So P of n equals 10 times 2 to the n is a solution to this recurrence relation. Can we prove that this is a solution? Can we prove that this always gives us the correct P of n? And if so, what technique could we use to prove it?
So we have a base case, and then we just need to prove that n plus 1 is true as well.
Yeah, we can prove this using mathematical induction. So we could make a proposition. Let Q of n be the proposition that the population at time n is equal to 10 times 2 to the n. And we want to prove that this proposition is true for all n bigger than or equal to 0. And if we want to prove this with mathematical induction, we have to do two things. One, we have to prove a base case. So we need to prove Q of 0 is true. Well, Q of 0 is the proposition that the population at time 0 equals 10 times 2 to the 0. Well, we know the population at time 0 is 0, and 10 times 2 to the 0 is equal to 10 times 1, which is equal to 10, and so this is true. So it's pretty easy to prove that, this proposition is true for n equals 0. To prove the rest of it, we need to prove the inductive step. Prove that Q of n implies Q of n plus 1, where n is bigger than or equal to 0. Well, step 1, we'll assume Q of n, that's a hypothesis, Step 2, what does Q of n say? Q of n says the population at time n equals 10 times 2 to the n. That's the definition of Q of n. Well, if the population at time n is 10 times 2 to the n, and we know the population doubles every hour, then we know the population at time n plus 1 will be 2 times 10 times 2 to the n. That's using formula 2 and the fact that the population doubles every hour. And now we can do some algebra and observe that 2 times 10 times 2 to the n is equal to 10 times 2 to the n plus 1. That's just algebra. And we've just proven the population at n plus 1 is 10 times 2 to the n plus 1. Well, that's what the proposition Q of n plus 1 says. Q of n plus 1 says population at time n plus 1 is 10 times 2 to the n plus 1. And we've just shown that's true. So we've proven Q of n plus 1 because that's what statement 4 says. Therefore, Q of n implies Q of n plus 1 for n bigger than or equal to 0. And therefore, since we have a base case that proves Q of 0 and we have an inductive step that proves Qn gives Qn plus 1, Q of n is true for all n bigger than or equal to 0. That's mathematical induction applied to steps 1 and 2. And Qn is the proposition that Pn equals 10 times 2 to the n. So therefore, P of n equals 10 times 2 to the n for all n bigger than or equal to 0. And that's what we were trying to show. So this is a formal proof that this is a solution to this recurrence relation. And if it feels like there was nothing going on there except moving a bunch of definitions around, you're exactly right. At this level, the recurrence relation itself is almost an inductive proof of itself. Base case and inductive step, how we get from n to n plus 1. So it's how we walk the journey from here to this conclusion that this is a solution, right? That's the lesson of this part. And it's an exercise in definitions and understanding, you know, this is a proposition about this formula being equal to that expression, and so on. So this is I think a really good thing to kind of review and think about and talk about and ask questions about, you know, somewhere over the next few weeks. But we're not going to do this for every relation we come up with. This is just an example. Yeah, go ahead.
Could you please put up the stage 2 again, please?
Yeah.
Thank you.
Mm-hmm.
For step 3, did I say 100 or 1,000?
Where's that?
In step 3, the P of n plus 1 equals 2.
2 times 10 times 2 to the n.
Oh, that's a 10.
Yeah. That's just what P of n is, right? So P of n is equal to 10 times 2 to the n.
Thank you.
Mm-hmm. All right, other questions? We're going to do some other recurrence relations. And we're not going to go through this inductive proof. I just want you to kind of see there's a connection between the method of mathematical induction and these kinds of ways of thinking about quantities or properties. Alright, let's talk about bunnies. Anybody here ever have a pet bunny?
I had a hamster at one point.
Probably similar experience. Bunnies are awesome. They're terrible pets if you're a renter because they will destroy your property. But if you're okay with that, they're awesome pets. They're like smart, and I grew up with cats, and bunnies are very different from cats. Like a cat, if you want it to stop doing something, you just make a loud noise and it'll run away. A bunny, you make a loud noise, it'll stare at you and it'll thump really loudly because it thinks you're trying to signal it or something, you know. So they're interesting animals, and I had a bunny a while back. It was a big bunny. I mean, like really big, and pretty smart. Centuries ago, a fellow named Fibonacci was studying rabbit populations and looking at how population of rabbits increases over time. And this was almost a footnote in a much larger text, but it became the thing that he's remembered for. And so let's reproduce his thought experiment and look at a population of idealized theoretical rabbits. And so we're going to make a few assumptions. The first assumption is these rabbits are immortal, so they live forever. I'm going to count pairs of rabbits as a single unit, just to simplify things. So when I write down, you know, that we have one rabbit, I really mean a pair of rabbits. Or you can think of rabbits as, you know, reproducing on their own, like tribbles in Star Trek or something. But I'm going to really think about groups of, you know, 2 rabbits that can reproduce. I'm going to look at this population month by month, and I'm going to use the following simple rule. After 2 months, each rabbit or each pair of rabbits has 1 offspring. So newborn rabbit doesn't reproduce. Rabbit that's 1 month old doesn't reproduce. When it gets to be 2 months old, it'll reproduce, create a new offspring. And the next month it'll create another offspring, and every month after that it'll have another offspring forever, because the rabbits are immortal. And we want to see what the population of rabbits looks like over time, beginning with a single rabbit or a single pair of rabbits. So time 1, we have 1 rabbit. So let me mark off time like this. And we're gonna go by 1 month intervals. And so I'm going to record age. I'm going to record time going down like this, and I'm going to record age going across. So we have 1 rabbit who's newborn at time 1. A month later at time 2, this rabbit is now a month older. And the whole population still just consists of this 1 rabbit. A month later, this rabbit is now a month older. Now it's 2 months old. And remember, 2 months is the magic mark at which rabbits start reproducing. So at this point, this rabbit has 1 offspring, and we have a newborn rabbit in the population. And let me put some things here to line things up. Okay, a month later, what happens? This rabbit has gotten a month older. This rabbit has gotten a month older. And since this rabbit is past, you know, the age of reproducing, it has another offspring, and we have another newborn rabbit. The next month, everyone gets a month older. But at this point, we've got 2 rabbits that are old enough to reproduce, and so we get 2 new rabbits into the population. And so we can just keep doing this. We can keep aging the population, And at this point, there's 3 rabbits that are old enough to reproduce, so we get 3 new rabbits in the population. And let's just do this one more month. And so everyone gets a month older. These 2 get a month older. These 3 newborns are now 1 month old. And now we have 2, 3, 4, 5 rabbits old enough to reproduce, so we get 5 new rabbits in the population. And we can keep doing this. So let's look at the total population at each point. In the beginning, we had 1 rabbit. After a month, we had 1 rabbit. At time 3, we had 2 rabbits. And then we had 3 rabbits. And 2, 3, 4, 5 rabbits. And then 3, 5, 6, 7, 8. And then finally at T7, 5, 8, 10, 11, 12, 13 rabbits.
The Fibonacci.
That's the Fibonacci series. So named because of Fibonacci, who was studying this theoretical population growth. And if you've encountered Fibonacci series before, it was probably by way of a recurrence relation. Fibonacci numbers have the following property. The nth Fibonacci number is the sum of the previous 2 Fibonacci numbers. And this works for n bigger than or equal to 2. And then we just have f1 equals f0 equals 1. And so you can write out this series by saying, let's start with a pair of 1s and just keep adding the previous 2 values. 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, and so on. And it's a very famous series.
Is it Fortran that you can create the Fibonacci sequence in like 1 line?
We can kind of do it in 1 or 2 lines in C. I'll show you some code for that in a bit.
One that's like super recursive base.
Yeah, and
Right now.
I don't know a particular Fortran function for doing that, but a lot of languages probably have a Fibonacci function that you can just call. But why is this related to rabbit population? Why are we getting this growth in population that conforms to this recurrence relation? And if you think about the mechanics of population growth here, it pops out pretty easily. So let's imagine we were trying to find the population at time 8. There's 2 things that constitute the population. The first is, each generation is going to get 1 month older and is going to appear in this next column. So we're going to have a 1, a 1, a 1, a 2, a 3, and a 5. So one part of our population is going to be this. The second part of our population is going to be the part that becomes newborn. The population of rabbits that are just born in this time period. And where does that come from? Well, it comes from the number of rabbits that were at least 2 months old. That's this. Whatever this sum is, that's going to be what becomes the new population. Sorry, I did that wrong. It's this. Right? It's at T8, the population that's at least 2 months old, that's going to be this new population number here. So we're going to do 5, 8, 10, 11, 12, 13. So we're going to have a 13 in here. So the population at time 8 is going to be the sum of 2 things. It's going to be the sum of this population, which was what? That was the population at time T7. plus the sum of the population that's at least 2 months old, which is the population that was 1 month old here, which was the entire population at time t6. And so the population at time 8 is going to be the sum of those. Right? This is the population from a month ago that did not die because they're immortal. And this is the number of rabbits that were in the population 2 months ago, which is the exact number of new rabbits that we have in the population. So at time 8, this is the number of rabbits we had at time 7 plus the number of new rabbits. And so the total population that we get, and this will be 21 here, the total number of rabbits we get at time t follows this recurrence relation. It's the sum of the population at the 2 previous time steps. And so that's where the sequence was developed from, was by thinking about this and where do these numbers come from. But once you have this sequence, you start to find all kinds of wonderful properties in this. And so one property of this is that if you take any number and you square it, and you take a pair of numbers on either side and you multiply them, these are always within 1 of each other. Sometimes the square is smaller, sometimes the square is bigger, but they're always within 1. And that's kind of a cool artifact. Another thing is, if you pick up a pine cone or a sunflower or you know, a number of different things that occur in nature, and you count, for example, the number of seeds starting at the middle of a sunflower going out in the spiral till you get to the end, it's generally a number from the Fibonacci series. The number of petals on a flower, usually a number from the Fibonacci series. These pop up all over nature, not just in rabbit populations. They pop up in nature because the way that a flower grows, the way that a pine cone develops with you know, the shingles overlapping each other and so on, those are growth processes. And rabbit population in this context is a growth process. And the Fibonacci series pops up in all these different places. The other thing is, if you take consecutive Fibonacci numbers and look at their ratio, well, 1 over 1 is 1, 2 over 1 is 2, 3 over 2 is 1.5, 5 over 3 is 1.67, 8 over 5 is 1.6, I think. I think I did something wrong somewhere. If you keep working this ratio, you get closer and closer to a number. 55 over 34 is 1.61764. And this gets closer and closer to something called the golden ratio. And if you want to go down a fun rabbit hole, Google that.
Is that the whole, if you have 3 items, or if you have 2 things and you have to place them on the wall, you don't use 2 over 3, you use some...
Yeah.
ratio?
So this pops up in art, it pops up in music, so there's a better approximation of its value. And it's exactly equal to a 1 plus square root of 5 over 2. And it's the solution to this equation. And it's a ratio in that this total distance relative to this longer piece is the same ratio as the longer piece to the shorter piece. And so it's the sweet spot.
My buddy works and he does like CAD drawings and whatnot for an electrical company.
Mm-hmm.
And when they have to place 2 lights on a wall, say at the edge of a wall,
Mm-hmm.
they don't place it 1 at 1/3, 1 at 2/3.
Right.
They use the golden ratio to place them because it's much more aesthetically pleasing.
Yeah, absolutely. And you know, Leonardo da Vinci, if you look at any of his creative works, they're filled with this golden ratio. it's a very aesthetically appealing way to scale things in 2 dimensions. Very aesthetically appealing to humans. And right, so this is the ratio that pops up in flags. It pops up in music. It pops up if you listen to a piece of pop music and you measure out how long the song is and how long it takes to get to the bridge between the first part and the second part. It's generally very close to that golden ratio. It pops up in nature, pops up in painting, and it's just, it pervades the entire universe as far as we know. And it, pops up in the study of population growth. So it's a really cool way to take something that starts off kind of purely mathematical, and we can certainly go down lots of rabbit holes of the pure math aspect of this, but it also ties into a lot of things about art and beauty and perception and things that people have either known or have leveraged unknowingly throughout time in the creation of paintings and artworks and structures and so on. And it pops up in natural objects. And so that's a fun thing to go down. And if you like any YouTube channels like Numberphile, they always have videos related to Fibonacci series and golden ratio, golden mean, things like that. All right, so let's take a 5-minute break. We'll come back and look at some code for Fibonacci series, and then I'll go through our last example of recurrence relations, which will be towers of Hanoi, and then we'll go on to starting to look at counting if we have time. So yeah, let's do a 5-minute break, and we will come back at 2:23.
Okay. Yeah, they're upstairs. I don't think that card's full anymore, but this would be.
Okay.
He still has about 20 minutes to go. I like that too.
Alright, I'm back. Weird stuff going on. Alright. Oh, let me do a Fibonacci series. Do some Fibonacci code first. Just for completeness. So here's a recursive function for finding the nth Fibonacci number. If n is less than or equal to 2, we return 1. Otherwise, it's just the n minus first plus the n minus second Fibonacci number. And we return that. And that's you know, an extremely simple function. It's basically one line that does some calculations and a base case that just returns 1 if we look for the first or second Fibonacci number. And if we run that, you know, it works great. It generates 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, the first Fibonacci numbers we generated. But this gets really slow, right? We get up to 44 and it's taking a really long time to get to the next number. Fib 46 is just the sum of these two numbers, but it's taking a really long time. It's taking a long time because we're doing recursion. And, you know, to apply this formula to find the 47th Fibonacci number, we need to know the 46th and 45th numbers. And to find the 45th, we need to know the 44th and the 43rd. And to find the 44th, we need to know the 43rd and the 42nd. And there's a lot of calculations we're making to calculate the 47th Fibonacci number. And, you know, it finally finished, but the 48th is taking even longer. And so this is a case where writing the recursive function that uses the recurrence relation is pretty straightforward, but it ends up being a really expensive way to do the calculation. And so here's a similar version, right? If n's less than or equal to, return 1. Otherwise, just calculate Fibonacci of n-1, n-2, add them. But I have an evil global called count. And every time that I call my Fibonacci function, I'm going to increment count. So I'm going to keep track of how many times I make these calls to my fib function. And in addition to printing out the nth Fibonacci number, which I call answer, I'm going to print out the number of times that I called answer.
This is a really terrible way to calculate Fibonacci, right?
Well, it's easy in terms of writing the code, but it's pretty inefficient. And we can see the inefficiency by looking at how many times we end up calling our Fibonacci function. And we end up calling our Fibonacci function about the same number of times as the value of the Fibonacci number we're trying to calculate. So the reason that Fib 45 is going to be so slow is because Fib 45 is so big, and that's how many times we have to recursively call this function. And there's things we can do to speed this up, but without doing something fancier, which we call dynamic programming, which is next week's topic in CSE215. Without doing that, this just gets slower and slower. And if we wanted to calculate, you know, the 80th Fibonacci number, it would probably never finish. There's just not enough cycles in the universe to get there. Actually, 80 would probably finish, but 800 definitely not.
You overloaded your integer there too.
Say again?
You overflowed the integer there too.
Yeah, you can use longs and stuff.
Yeah.
Alright, so we'll play around with that more in CSE next week. So now let's talk about Towers of Hanoi. And so Towers of Hanoi is a game that you can play. And one of my former students after graduating got me a nice wooden version of this game. I used to use like cut up pizza boxes and pencils. So they got me like an upgraded version. So here's the setup. You have a series of wooden squares. In the original version, these are discs made out of jade, but you know, I've got wooden squares, and they come in different sizes. So they're all different sizes, and so some are larger and some are smaller. And the idea is you start off with a set of these squares sitting on one of these sticks. And they should be organized from largest to smallest. And you're never allowed, for example, to put a larger disk on top of a smaller one. That's not allowed. You can only put smaller disks on top of larger ones. So that it always, you know, kind of like looks like that, going from bigger to smaller as you go up. And the goal of the game is to move this pile of discs from one stick to another. And you have to follow a set of simple rules. And the first rule is, you know, you can only put small discs on top of bigger ones. The second rule is you can only move from the top of a pile. And the third rule is you can only put down on top of whatever's already on a pile. So I can't take this and put it underneath this disc, for example. And I can't take this and put it here because now I have a bigger disc on top of a smaller one. But I could take this and I can move it over here because it's not on top of a smaller disc. And I only took it off the top and I put it on top of whatever was already on the pole. And so you're trying to move this stack from, say, you know, this leftmost stick to some other stick. And so I could take this and I could take this and I could move it on top of here. That's legal. But that doesn't buy me much. I could take this and I could move it over here. That's legal. I could take this and put it on there. That's legal. I can bring this over here. I can take this and I can put it either here or here. I'm going to put it here. And now I can take this and put it here. And now I can take this and put it here. And I'm done. I've solved the puzzle. I moved my pile of discs from this stick to that stick. And so the legend, one of the legends about this game is that there's a cave with monks living in the cave, and they've been living there since the beginning of time. And at the beginning of time there was a pile of 64 jade discs, and these monks work day and night to move the discs from one stack to another, following the rules of this game that we just went through. And the story is that when they finish moving the entire stack from one stick to another, that's the end of the universe. So they're marking the passage of time, the aging of creation. And when all 64 discs have moved, the universe is done. So that's the basic setup for this. And so a good question to ask is, you know, how many moves does it take to move a stack of discs from one stick to another? Because, you know, according to the legend, that's how much time we have in the universe. Well, let's go with 3 discs again. And let's see how few moves I can get away with. So I'm going to go 1, 2, 3, 4, 5, 6, 7. So 3 discs. Three discs I can move in 7 moves. If I start with 2 discs, it's even easier. So 2 discs, and let's say I want to move from here to here, so I'm going to do 1, 2, 3. So 2 discs takes 3 moves. If I have a single disc, Well, that's the easiest of all cases. How many moves does it take to move my disk from here to here? Just takes one move. So, does anyone see a pattern in these numbers so far?
We're fine. So far. Yes, but I'm not sure.
What do you think you see?
Well, I see if I jump from 1 to 3, that's a jump of 2 moves, and from 3 to 7 is a jump of 4 moves, so we're dealing some kind of power of 2 thing.
Mm-hmm.
I think.
So the increase seems to be increasing powers of 2. And along the lines of powers of 2, sometimes when you try to find a sequence in something, if you don't look at the actual thing you're thinking about, but you look near it, you might find a sequence. And so, example, if I add 1 to each of these, I end up with 2, 4, and 8. And that looks familiar. Alright, so this number 1 is actually 2 to the 1 minus 1. This is actually 2 to the 2 minus 1. This is 2 to the 3 minus 1. In consecutive powers of 2, that's where we get that increasing difference, where the difference itself is a power of 2. So I think it's a good intuition that something exponential going on here, something related to powers of 2. And so if we had 4 disks, well, this was a jump of 2, 4, we might go up by 8, would get us to 15, or 2 to the 4th minus 1, 15. 15 looks like, you know, that might be reasonable. So let's see if we can solve this in 15 moves. And I'm going to use some bigger disks to make it clear what goes on top of what. Alright, we got 15 moves in order to move this pile from one post to another. Alright, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 3, that's tricky. I got 8 moves used. I got 7 left. 9, 10, 11, 12, 13, 14, 15. Alright, so this pattern seems to hold. And so theoretically, 5 disks should be doable in 31 moves. And I'm going to show you how to do this with 5 disks, but I'm not going to go through all of the moves. We're going to do something a little different. We are going to look at a recursive solution to this question of how many moves does it take. So suppose we know that we can move 4 disks in 15 moves. Let's take that as given, fix that in our minds. 4 disks, we can move them in 15 operations. Well, now I've got 5 disks, right? 1, 2, 3, 4, 5. And I want to move those, say, from here to here. Alright, I'm going to do 3 things. First, I'm going to move these top 4 disks from here to here. Now, I'm not allowed to just pick them up and move them. I have to follow the rules of the game. But following the rules of the game, I know that I can move these 4 disks from here to here in 15 moves. Because having this extra large disk sitting here does not change any of my moves. This is smaller than every disk, and it's at the bottom of a pile. So whatever I can do with a game of 4 disks, I can do with a game of 4 disks with a big disk sitting here on the bottom. So I know that in 15 moves, I can take these top 4 disks and move them from here over to here. And now with one more move, I can take this largest disk and put it in the middle. And since I know I can move 4 disks in 15 moves, with another 15 moves, I can take these 4 disks and move them over to here. And I've solved my 5-disk puzzle. And it took 15 plus 1 plus 15, 31 moves. So my recurrence relation here, let m of n equal the number of moves for n disks, and we know that m of 1 is equal to 1. The recurrence relation we can get is m of n is equal to m of n minus 1 plus 1 plus m of n minus 1. Or if you like, 2 times m of n minus 1 plus 1. And if we think, you know, maybe m of n is equal to 2 to the n minus 1, well, that satisfies this relationship. M of 1 would be 2 to the 1 minus 1, that's correct. And m of n plus 1 would be 2 to the n plus 1 minus 1, which is twice 2 to the n plus 1. So we can discover this recurrence relation, right? The number of moves for n disks is twice the number of moves for n minus 1 disks, plus 1 more. We discover that, and we could solve this recurrence relation by setting number of moves equal to 2 to the n minus 1, and we could thereby prove that, you know, this formula tells us the number of moves. And we could prove that was true using a mathematical induction proof, but we're not going to do that. But we can also get an algorithm from this. The logic that we worked through to discover how many moves it takes to do n disks in terms of how many moves it takes to do n minus 1 disks, that also discloses an algorithm for solving this puzzle. If I wanted to solve this puzzle, for 6 disks, how do I do it? Well, if I know how to solve it for 5 disks, which we just did, I'm going to take those 5 disks and move them over here. That's going to take 31 moves. And then I'll take this disk and put it in the middle. Now we're up to 32 moves. And then I'll take these 5 disks and move it from there to there with another 31 moves. That's 63 moves, and we've solved the puzzle. So this is another example where recurrence relations, mathematical induction, and algorithms all kind of come together, and they're all kind of the same thing. So let's look at some code. Alright, so here's a recursive Tower of Hanoi demo. And I'm going to write a function called tower that basically tells me how to move this many disks from this post to that post. And I'm also telling it which post is not in use, right? What the other post is. So I'm thinking of my post as being numbered 1, 2, and 3. And if I want to move from post 1 to post 2, I'll call tower with a number of disks, a 1 and a 2. And then for the convenience of the code, I'm also telling it what the number of the third disk is. The one that's neither the source nor the destination. We can figure that out, but I'm making it a little simple to understand the code. So I gotta move 8 disks from stick 1 to stick 2, with stick 3 being spare. And I'm also going to count the number of moves in here, just for fun. So I've got a global for moves. So what do I do, right? Here's my tower function. Move this many disks from this stick to that stick. And this is the open or spare stick. Alright, so there's a base case. If the number of disks I have to move is 1, it's really simple. Just move from the source disk stick to the destination stick. So if I say, hey, I want to move 1 disk from stick 1 to stick 3, how do I do that? Take the disk, move it from stick 1 to stick 3, we're done. If I say I want to move 1 disk from stick 3 to stick 2, what are the moves I make? Take 1 disk from stick 3, move it to stick 2. That's the base case, right? That's the easy one. If your whole task is to move a single disk, just move it, right? So if num is equal to 1, just do that move. And move is just a function that's going to print out what move I'm doing. Otherwise, how do we do this? Let's move 1 fewer disks from the source stick to the open stick. And then move 1 disk, which will be the biggest one, from the source stick to the destination. And then move the remaining num-1 disks from where we moved them up here to the destination. And that should let us move all the disks. And my move function is just a print. It's just going to print out where I'm moving from and to, and it'll print out 5 per line. So I can call tower with, a target of 8 disks. And there's our solution. These are the moves that you would make. Move from stick 1 to 3, 1 to 2, 3 to 2, 1 to 3, 2 to 1, and so on. And when you're done, you should have solved the puzzle. And it's telling us at the end, the total number of moves it made was 255. Well, that's 2 to the 8th minus 1. So that matches our calculation. So let's try this with 4 disks. Right, there's our solution for 4 disks. So let's see if this actually works. So this is stick 1, 2, and 3. So I'm just going to follow this first line of instructions, which says move from stick 1 to 3, move from 1 to 2, move from 3 to 2, move from 1 to 3, and then move from 2 to 1. That was our first 5 moves. Next 5 moves say move from 2 to 3, 1 to 3, 1 to 2, 3 to 2, don't destroy your game, 3 to 2, and then 3 to 1. And you have to watch me and make sure I don't do illegal moves. And then the last 5 moves, move from 2 to 1, 3 to 2, 1 to 3, 1 to 2, and last move 3 to 2. And guess what? We solved our puzzle. And to figure out this sequence of moves was basically 3 lines of code. The rest is like setup and preamble and wrap up and all that. It's basically 3 operations. Yeah, someone had a comment?
I said it was amazing.
It's pretty cool, I think. And so we can try to cause the universe to end by moving 64 disks. And here's the set of moves we would make. And if we follow those moves carefully enough, we'll end up moving all 64 disks from stick 1 to stick 2. But it's going to take a while.
It's like 1 times 10 to the 18th or something.
Yeah, so how big is this? 2 to the 64th minus 1. Well, it's a big number.
1.8 times 10 to the 19th.
Yeah. So, right, so that's the number. If you did 1 disk per microsecond, let's suppose these are really fast monks, right? 1 disk per microsecond, so we would do 1,000,000 moves per second, which means it'll take 10 to the 13th seconds. If you divide by 3,600, it's that many hours. If you divide by 24, it's that many days. If you divide by 365, it's that many years. So over 500,000 years to complete that game, if you're doing 1,000,000 disks per second. If you're doing 1 disk per second, it's 500,000 million years to complete the game. So the universe has some time left in it. Nonetheless, finding out which moves to make is trivial if you have a computer, right? And this will just, happily keep printing and giving out instructions until it's done. And then it'll report, that it made a total of, 1.8 times 10 to the 19th moves.
But that program will take roughly the amount of time that we just calculated, right?
Yeah, so if I could print out 1,000,000 instructions per second, then this would take, 500,000 years to finish. It's a long time.
So we won't be seeing that answer.
We won't be seeing that answer today, yeah. And I'll be resetting the server long before then. But it's a cool theoretical result anyway.
Weirdly enough, it kind of reminds me of Hitchhiker's Guide to the Galaxy.
Ah, yes. Excellent.
I think everyone's read that but me.
I have not read it completely, but one of my my bosses on Wall Street fell in love with it, and it became like almost a religious thing for him, which was kind of cool to watch. And so I read it a little more then. And years ago, when I worked for Department of Defense, I had a coworker who was really kind of eccentric, and he had a copy of this and was always telling me about it. And yeah, it's a popular book. All right, so I'm going to stop this so that the universe doesn't end. So recurrence relations, right? They pop up in a lot of unexpected places, and let me give you one more example of this, and then maybe we'll call it a day, because it's going to be a week before we come back, and I don't know if I want to start something new right then. But let me give you one more example of a recurrence relation related to bit strings. And the question is, how many n-bit strings? So, you know, strings consisting of n bits, ones and zeros, do not have any consecutive zeros. So, you know, picture a 5-bit string. So any combination of 5 ones and zeros. We know there's 32 combinations. But how many of those do not have a pair of zeros next to each other? And so, for example, 1 bit, well, we only have a 0 and a 1. Those are our only 1-bit strings. Neither of those has a pair of consecutive zeros. And so we have 2 1-bit strings that satisfy this requirement. If you have 2-bit numbers, we have 0, 0, 0, 1, 1, 0, and 1, 1. And 3 of these satisfy this requirement. 0, 0 fails. If we look at 3-bit numbers, there's 8 possible 3-bit numbers. And which of these satisfy our requirement? Well, this one, this one, this one, this, and this. And these other 3 have, you know, at least 2 consecutive zeros. So we have 5 strings like this. Okay, I don't want to write out all of the 4-bit strings because there's 16 of them. But let's think about this a little differently. Suppose we have a 4-bit number. So a 4-bit number looks like this. 4 bits. And each bit is a 0 or a 1. And let me make a function. P of n equals number of n-bit strings without consecutive zeros. So here's what P of n looks like for these values of n. So we want to calculate what P of 4 is. How many 4-bit strings don't have consecutive zeros? And there's exactly 2 possibilities. When I write a 4-bit string, it could be that my string ends with a 1. Or it could be that my string ends with a 0. But those are the only options, right? So let's look at this. Let's look at this first option. Well, the last bit's got to be either a 1 or a 0, right? So let's look at this first option. Suppose my number ends with a 1. Do I know anything about this 3-bit pattern of 1s and 0s? I know it's 3 bits, it's made of 1s and 0s, but what else do I know about it? Assuming that my 4-bit number does not have any consecutive zeros.
All of the same properties of the 3-bit numbers.
Yeah, this can be any pattern that does not contain consecutive zeros. If there's no consecutive zeros here, there's no consecutive zeros there. And if this is a 4-bit number with no consecutive zeros, this must be a 3-bit number with no consecutive zeros. So how many numbers without consecutive zeros are in this form? It's just P of 3. It's the number of 3-bit strings. I'm going to have exactly 5 of them. Could be 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, or 1, 1, 1. On the other hand, suppose I have a number in this form that ends with a 0. And I want this whole 4-bit number to not have any consecutive 0. What do I know about this number besides the fact that it ends in a 0? Is there any other information?
The other 3 digits have to follow the same rule, except the last one has to be a 1.
Ah, the last digit has to be a 1. Because if this is a 0, we've already got a pair of consecutive zeros, and that's not allowed. So if we have a 4-bit number ending with a 0, this has got to be a 1. And now we've got 2 bits left. And this can be any 2-bit number that does not have consecutive zeros. And how many 2-bit numbers do we have without consecutive zeros? That's just P of 2. And so all of our numbers with 4 bits that don't have consecutive zeros are either in this form or that form. There's P of 2 in this form, there's P of 3 in this form. So the total number of bit patterns we have is the sum of those, P of 3 plus P of 2. And now we're off and running with the bunnies. Say again?
This looks like Fibonacci.
That's Fibonacci. And it's starting with, 2, 3, 5. Those are the first few terms of the Fibonacci series. And we got the same recurrence relation. So the Fibonacci series also tells us how many n-bit strings don't have consecutive zeros. And we've seen that for 4 bits. But do we know that this pattern also holds for 5? Well, we haven't shown that yet. But we could. We could say a 5-bit number ends with either a 0 or a 1. If it's a 0, the number of bit patterns that fit in this pattern is P of 4. If it ends with a 1, then if it ends with a 1, this can be anything, so this is P of 4. If it ends with a 0, this has got to be a 1, and the number of ways to fill in this is P of 3. And so we could show P of 5 equals P of 4 plus P of 3. But what about P of 6? This does not prove that P of 6 is equal to P of 5 plus P of 4. But we could prove it by doing this exact same thing with 6 lines and putting a 1 and a 0 and saying P of 4, P of 5. And if I wanted to prove that this formula was true for P of 10 equals P of 9 plus P of 8, I could do that by repeating this process a few more times. But if I wanted to prove that for any n bigger than or equal to 2, P of n equals P of n minus 1 plus P of n minus 2, could I do that? And I'll give you a hint, the answer is yes, but the bigger question is, how would I do that? What technique would I use?
Induction.
Mathematical induction. It's always the right answer. I would make a proposition that P of n is equal to P of n minus 1 plus P of n minus 2. I would show it for a base case, like this, and then I would prove that P of n, or whatever I call this proposition, implies the next proposition. And how would I make that leap from n bits to n plus 1 bits? I would do this trick once. And I would say, since I know that the formula is correct for n minus 1 bits, right, this is the formula for that, and I know it's correct for n minus 2 bits, maybe I'm doing strong induction, and so I get a formula for that. I add them together, that tells me how many bit patterns I have for n bits, and that's my inductive step. And you put that all together in the right way, you wave the mathematical induction wand and say, therefore, by mathematical induction, and bingo, you can prove this formula works for all n. Right? That's mathematical induction. And it just pops up again and again and again anytime that you have something like this that you can do in specific cases, and you can see that there's nothing magic about the number 4. There's nothing magic about the number 5. Right? I could do this if I tried to do it for 10 bits or 10 billion bits. It would be exactly the same process. That's when you can usually pull in mathematical induction and turn that idea of, I can do this for any number. You can turn that into a proof which says, and in fact, this is absolutely true for any number. So that's mathematical induction. All right. So I'm not going to start a new topic right now because we've only got 5 minutes. Monday's a holiday, so we won't meet again until a week from today. But when we come back Wednesday, we'll talk about homework questions for the current homework. And then we're going to start talking about counting and counting arguments and things that we can do by basically counting 1, 2, 3, 4, 5. Very straightforward process, but we can start asking, you know, let's count how many ways certain things can be done. Let's count how many ways I can arrange these 3 objects on this piece of paper. I could do it like that, or like that, or like that, or like that. You know, how many ways can I do that? So these are counting questions, and we're going to spend probably about a week looking at different ways of analyzing these counting questions, and it's going to lead us into some areas related to probability. It's going to lead us into something called the pigeonhole principle, which is a basic counting argument. And it's going to let us see some very unexpected properties of some different systems. And we'll conclude all of that with something called Pascal's triangle, which is an amazing discovery of properties among numbers, and it ties into multiplying polynomials, probabilities, factorials, primes, all kinds of other things are tied into this one simple structure of numbers.
Question.
Yeah.
Students last term said they did a PA2, but are we doing a PA2?
No, so I think last term I had a PA2 where they actually constructed Pascal's triangle. I don't think we're going to do that this quarter, though. I just did one programming assignment, and we'll call it good with that. Partially because, you know, fall term is 11 weeks, and we lose some time for Thanksgiving, but winter term for us is technically 9 weeks because we lose 2 Mondays, and it's a Monday-Wednesday class, so we're going to call it good with just the one programming assignment. But if you want more programming to do, I'm happy to give you some other things to work on. But you probably got enough. All right, so
Would you be able to post like the document, the EI document for that Pascal triangle programming thing, just in case we want to try it out?
I don't want to post it on Canvas because inevitably someone will think it's an assignment. But the goal was basically to print out Pascal's triangle, and when we get to Pascal's triangle, we'll go over how the algorithm was supposed to work, and it's a simple addition process. And then if you want to write a program to do that, I think it'll be pretty straightforward at that point. But if you send me an email, I'll send you a copy of the PDF if you like.
I was arguing with some students on the Discord chat over a way to make the triangle look like a triangle.
Yeah, I saw that. It's a good challenge, because if you don't know how big the last row is, then you don't know where to center the first row, right?
Right, yeah.
But it's an interesting thing. On the other hand, if you printed it out upside down, it would be easy. But that's that whole entropy, time goes in one direction kind of conundrum, which is another topic altogether. All right, I'm going to leave it with that. Take a look at the induction homework. I've got office hours tomorrow and Friday and Tuesday mornings, so feel free to catch me in there if you've got questions. Hope everybody has a good rest of the week. If I see you in 222, great. If not, have a good one, and I'll see you next week.
Have a good day.
Thanks, you too.
Good day.